Okay, so, right, what we have here are some further practice questions given by the exam board, and we're going to go through those now. I want you to notice again how many times they're asking you to identify algorithms within pseudocode and fill in questions based on those algorithms. Question 1. The subroutine below is used to authenticate a username and password combination. Array indexing starts at 0. Okay, so sometimes they'll start them at 1, sometimes they'll start them at 0. This is 0, 1, 2. This is 0, 1, 2. It's worth, in your exam, just writing the indices next to any array entries. Just helps you, particularly if these are longer in length. It just also reminds you whether you're using 0-based indexing or 1-based indexing. And it asks us to complete the trace table for the following subroutine call. So authenticate, so that's going to be this subroutine here. And then we're putting Alice into our user. So this is our, remember, argument, and these are our parameters. And then woof 2006 is going to go into here. So let's go through. So we've got an assignment of our two arrays, US and PS, usernames and passwords, I suppose. And now what does it do? It sets Z is 0, so we're going to write 0 in here. And then correct, it gets assigned to false, so we're going to write false in here. So we've done that. Now we're on to here. Now look at this while loop. Remember, this while loop is going to go round and round and round in here while this condition is true. Okay, so we need to test this condition every single time we get back to the top of this while loop. So is Z less than 3? Well, 0 is certainly less than 3. So we're going to go inside and we're going to do the inside of this while loop now. Now we've got a decision to make. If user, now what is user? User is Alice. Is Alice equal to USZ? Well, Z is 0, so US 0, well, that's Dave. So if Alice is equal to Dave, it isn't. So therefore, we don't do this. We don't go into here. Instead, we go to this line here, line 12. Okay, so we're sitting at line 12 now. And it says Z is Z plus 1. So Z used to be 0. It's increased by 1, so now it goes to 1. And then we go back up to the while loop again, and we look, is Z less than 3? Is 1 less than 3? Yes, it is. It says if user, which is Alice, is equal to US1, and that is Alice. So that is true now. So this is true. So we're going to go inside here. Now there's another test now. If password, so pass, and pass was woof 2006, is equal to PS Z, and Z is 1, so woof 2006 is password, woof 2006, and this is 2006, and this is also true. So it now sets correct equals true. So it sets correct equals to true here. And now it's going to increase. Don't forget, once we finish this if statement, which we have now, it's going to go to this line here. You must follow this instruction, Z is Z plus 1. Just because you've got a true here, don't be tempted to stop. So Z is Z plus 1, 2, and then back up to the top of the while loop, and now let's check the condition again. If Z is less than 3, yes it is. 2 is less than 3. So if user, which is, again, Alice, is USZ, and Z is 2, so that's Bob, so that's not true. So it won't do that, and it will come down here again and increase Z to 3, up to the top of the while loop again. If Z is less than 3, it isn't, it's equal to 3, so this while loop will now not execute, and we'll go down to the end while here, and then we're going to return the value of correct, and the value of correct is true, so it's going to return true. All right, okay, so Notice it just said complete the trace table. It didn't say what it returned. Part B does. It says state the value that is returned by the following subroutine call, Bob ABF32. Now, if you sort of got the idea of what the username is doing, it's authenticating the user against their password, authenticate Bob against ABF32. Well, you can certainly see that Bob's password is this exclamation mark at 34E dollar. Then hopefully you would see that this will never happen, and if it will return the value of correct that was set at the beginning, which was going to be false. So that's going to be false. Okay, lines 7 and 8 in the subroutine. So I'm just going to take a copy of the subroutine now. Just going to do that. I'm just going to take a copy so that I can see it on the screen all at the same time. There it is. I'm going to move it down into this page so we can see that going on up here. Okay. Lines 7 and 8. Here we go. 7 and 8. So we're looking at these two lines. Could be replaced with a single line. Shade 1 lozenge to show how it corresponds to the correct new line. So this basically, in order for this line 8 to be executed, 7 must have been true. So in other words, both of these must have been true. And if both of them must be true, that corresponds to an AND. So it's either going to be B or C. We know for a fact it's not going to be this one. Okay, because that's OR. So we want an AND. And we want to make sure that correct, which means correct password, in other words, being authenticated, yes, it's the correct password. It's only set true if they are equal. So it is B that's going to be correct. A programmer implements the subroutine shown above. He replaces line 9. So this line 9 correct is true. With return true. So this just says return true now. And also replaces this with return line 4 with return false. Explain how the programmer has made the subroutine more efficient. Well, the point is here, if you remember when we went through the previous part of the question, this algorithm continued while z was less than 3. It kept going round. Z was 0, 1, 2, and then 3. When we'd already authenticated the fact that Alice had typed in the correct password, Wolf 2006. But nevertheless, it kept going through all the other users to see whether it was correct. So you can see that that's inefficient. It's keeping going around the other users, even though we've found the user that we're interested in the user array. So, explain how the program has made it more efficient. The algorithm no longer needs to check other users or other user password combinations once authentication, or once the found user, once the desired user has had their authentication checked. Okay? So the algorithm no longer needs to check other username and passwords. In other words, it's going to be returned as soon as you get a correct authentication. Question 2. The arithmetic effect of applying a left binary shift of 1 to a number is to multiply that number by 2. Okay, let's just remind you of that. Let's say if you've got a, let's say a denary number, okay, where you've got units, tens, hundreds, thousands, etc. So let's say we've got a number 213. If we left shift this, in other words, we shift everything left by 1 place, 2, 1, 3, and we put in our 0 to pad the zeros in because we always need to have this units column filled in, then we've multiplied by 10 by shifting left. Now if we do that with base 2, so that's denary, base 10. If we do that with 2's, well, we don't have units, we've got 1's, 2's, 4's, 8's, for instance. So let's say we've got this number 101, which is the denary number 5, and we shift that left by 2. Shift that left by 1 place. We get 1, 0, 1. So that 1 goes over here, this 0 goes over there, this 1 goes over there, and we pad the 0. This was 5, base 10. What's happened now? Well, we've now got 8 and 2, which is 10. So we have doubled it. In other words, we've multiplied by 2. So it is, indeed, a left shift is a multiplication by 2. So what do we do if we left shift by 3? Well, if we left shift by 3 in base 10, instead of multiplying by 10, we're multiplying by 10, then another 10, then another 10. So in other words, we're multiplying by 1,000. In base 2, we're multiplying by 2, and then multiplying by 2, and then multiplying by 2 again. So this is the effect is a multiplication of 8 by 8. 2 times 2 times 2 is 8. And with our example, we could see that that was the case because this is left shifted by once, twice, oops, 3 times. So if you can't remember what it should do, you could always work it out. Remember, these are 16s, these are 32. So we've got 32 plus 8, which is 40. And so 40, what did I multiply by? 8 5s are 40. So I did indeed multiply by 8. Question 3. A sound engineer is recording a singer. Describe why the sound must be converted to digital format before it can be stored on a computer system. Well, a digital format stores binary information, zeros and ones, zeros and ones, whereas an analog sound has continuous levels. So in other words, we've basically got some sort of sound wave in analog form. So this is the analog, and the digital version of that basically has samples done every so many milliseconds determined by the sample interval, and it turns this into a series of different levels of height. So each levels of height represents a different bit pattern in that, and so basically these would be different binary values. So a digital format stores binary information as zeros and ones, whereas an analog sound has continuous levels. So we convert each level, shown in diagram, to a different bit pattern. okay, which represents the approximation to the analog sound. Okay, part B. The sound engineer is using a sample rate of 2000 hertz. Okay, so we've got sample. If I was in the exam, I would perhaps get a highlighter pen. Sample rate of 2000 hertz, sorry. A sample resolution of 4 bits and a 5-second recording. Your answer should be in bytes. Okay, so let's remember our formulas. So a size in bits is equal to the sample rate times the sample resolution times the length in seconds. Okay, so the sample rate that's 2000, and the sample resolution is 4, and that's bits, times the length in seconds, which is 5. And this is bits. So if we want that in bytes, we need to divide that by 8. Okay, so divide by 8, cancel down. 4 goes into 8 twice. 2 goes into 2000 1000 times. We've got 1000 times 1 times 5, which is 5000 bytes. Okay, so remember, we need to do our calculation in bits and convert to bytes by dividing by 8. By the way, you could be asked for your answer in kilobytes, in which case that would be 5000 divided by 1000, so it would be 5 kilobytes. But in this case, they want bytes. The sound engineer usually uses a sample resolution of 4 bits, which enables sample to be stored as 16 different bit patterns. Why 16? Well, remember 2 to the 4 is 16. That's why that gets that. She wants to increase the number of bit patterns available from 16 to 32. So we want to increase this to 32. Okay. Shade 1 lozenge, which shows the minimum sample resolution in bits she can choose that will allow her to do this. Okay, so what is 32? Well, that's 32 is 2 to the 5. 2, 4, 8, 16, 32. So therefore, this is here. This is the sample resolution. So that's 5 bits. Part D. Shade 1 lozenge to show which of the following correctly states the effects of increasing the sample rate. Okay, so if you're increasing the sample rate, basically what you're doing in here is you're making these more narrow. Okay, so that's what's happening, and therefore you get more accurate conversion from analog to digital. So let's see what the questions are. Decrease both the quality. Well, no, if you're increasing the sample rate, it means you're doing more samples per second. You're going to get an increase in quality. So this, we're looking for increase in quality. But the expense of increasing the quality is also to increase the size of the file or the memory required. So let's have a look. Decreases quality? No, definitely not. Has no effect? No, it does. It increases quality, so that's fine. Improves the quality? Yes, it does. And has no effect on this? No, it doesn't. It does increase the size of the file. Improves the quality? Yes, and increases the file size. So that's the correct answer. Question 4. Complete the truth table for the OR logic gate. Remember, OR, you possibly should remember as either or. So if either or of the inputs are a 1, we get a 1. Otherwise, we get a 0. So this is either or. No, neither of those are a 1, so that's no good. For a 1, we get a 0. 0, 1, yes, we do get a 1. So or one of those, either that or that is a 1, so that's fine. Same here, same here. Okay, complete the truth table for the logic circuit shown below. So we've got A, B. This, remember, is an AND gate. and this is also an AND gate, and this is a NOT gate. You need to remember those. So let's have a look. If A and B are both 0, then the result of 0 or 0 is 0. So this would be a 0 here, because A and B are both 0. This is a 0, and A and B, this is also 0, but then we NOT this 0 to get a 1. So that's going to be a 1. X was a 0, Y was a 0. Okay, let's try this one. A is 0. Just delete those. A is 0, so we've got a 0 here, and B is 1. Well, 0 and 1 is 0, because they both have to be a 1 for an AND to output a 1. So that's a 0. B, remember, is a 1, but both of these have to be a 1, so that's a 0, and then we NOT the 0 to get a 1. So that's going to be that, 0 and 0. Now we've got a 1 and a 0, so let's see what happens there. So this is a 1, A is 1, B is 0, so that is 0 there. Both of these have to be a 1 in an AND gate, so that's going to be a 0. Both of these have to be a 1. We've got both 0, so that's a 0, and we NOT the 0 to get a 1. So they're again going to be 0, 0, 1. And now let's try our final thing, 1 and 1. So this is a 1 and a 1. Both of these need to be a 1. They are. So 1 and 1 is 1. So X is 1. And this is a 1, remember, because B is 1. This is a 1, because it comes down from here. 1 and 1, that's a 1. But that gets knotted here. So that's Y is a 1. But Z is knotted to a 0. Part C. A logic circuit is being developed for an automatic door system. The automatic door has 2 sensors, one on either side of the door, sensor F and sensor B. The door opens when either of these sensors is activated. So either. So that's either. Think of either as OR. So we want an OR to be activated here. Okay. So that's the either side of the door. The door system can also be turned on or off using the manual switch. The door will not open unless the switch is on. So the switch must be on. So this must be an AND. The output from this logic gate, so these must both be on. So if both of these are on, then okay. Next question. Question 5. The diagram below shows an 8 by 8. So we've got width is 8, and our height is 8. Black and white image. The image has been represented as a bit pattern with each bit representing a pixel. Row 3 has been represented as 0, 1. So row 3 starts off 0 here. So we've got a 0 here. 0, 1, 0, 1, 1, 0, 1, 0. So we can see that here that black is a 0 and white is a 1. So it's worth just writing that out like that perhaps. What is the binary representation of row 4? So row 4 is black, white, white, black, black, white, white, black. Okay, so let's just check that. Remember, black is 0. So black, yes, black, black, yeah, black, and white's a 1. So we do get our 0, 1, 1, 0, 0, 1, 1, 0. The image in the diagram is going to be changed so that each pixel can be any one of 16 different colors. What is the minimum number of bits? That's the color depth, which is so it's the color depth. So color depth of n gives 2 to the n colors. Now, the number of colors that we've got is 16. So we want 2 to the n is 16. What value of n gives us gives us this? Well, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and 2 to the 4 is 16. So the number of bits is 16. So this is our working. We put that in there, and our answer is 4 bits. Right, but the minimum number of bits that would need to be representing the entire 16 color image now. So the answer isn't 4 bits. That's the number of bits for each pixel. And the number of bits, the size of the image, is the width times the height, in other words, the number of pixels, multiplied by the color depth. And the color depth is 4, the width is 8, the height is 8, color depth is 4, and therefore we get 8 times 8 is 64, 64 times 4, 4 fours are 16, 6 carry 1, 6 fours is 24 plus the 1 is 25, 256 bits. Okay, and notice it says give our answer in bits. Question 6. Complete the binary addition of these three numbers. So 0 plus 0 plus 1, well, that's 1. No carry. This is all zeros. 1 plus 1 is 0 carry 1. 1 plus 1 is 0 carry 1. And 1 plus 1 plus 1 is 1 carry 1. 1 plus 1 is 0 carry 1. 1 plus 1 plus 1 is 1 carry 1. And 1 plus all these zeros is 1. Why is 1 plus 1 plus 1 1 carry 1? That's 1, and this is the carry 1. Well, if we look at this, this is 1 and 2. That's a total of 3. 1 plus 1 plus 1 is 3. This is 3. So you can see 1 plus 1 plus 1 is 1 carry 1. And if we did 1 plus 1 plus 1 plus 1, what's that? Well, that's 4. How do we represent 4? Well, that's 1, 0, 0, because we've got 1, 2, 4. So that would be 0 in one column, 0 in another, and then we carry the 1 over to the 1 over there. So let's show you what I mean by that. So let's say we had an example that said add up these 0, 0, 0, 1 plus 1, 1, 1, 1 plus 0, 1, 1, 1 plus 0, 0, 0, 1. And what we get here is 1 plus 1 plus 1 plus 1. Well, we just said that's 0, 1, 0, 0. So we get 0, carry a 0, that's this one. That's 0 carried. And then we carry a 1 over to here. Now we add these up. 1 plus 1 is 0 carry 1. Now how many we've got? 1, 1, 1, 1. So we've got 4 ones again. And that's 0, carry 0, and then carry a 1. So now we add up these. We've got 1 here. And then we've also got a 1 here. Okay, and we can see that that's right because this is 1 base 10. This is so this is 1, 2, 4, 8. So this is 15 base 10, and this is 1 plus 2 is 3 plus 4 is 7 base 10, and this is 1 base 10. If we added all those together, 15 plus 1 is 16. 16 plus 7 plus 8. What's that? 7, 8, 9, 24. Is this 24? 1, 2, 4, 8, 16. 16 and 8 is 24. So it does work out.